Sioux Falls Physics on the scene here. We're talking about some static and kinetic friction here. We have an office worker pushing a 115 kilogram filing cabinet across the floor. I guess couldn't find a dolly or anything to move it with, but this is a pretty strong lady. She finds that a force of 575 newtons is required to start the cabinet into motion, but then once it's moving, only 485 newtons required to keep it moving. And the problem is going to ask us here to determine those coefficients of static and kinetic friction. All right, let's start with our equation for frictional force. Okay, frictional force is equal to mu, the coefficient of friction, times the normal force. Okay, so let's go ahead and look at first the static frictional force that is existing here. Again, that static force is the force that's required to overcome the friction that is there to start the object in motion. So that goes into the 575 newtons that was mentioned as far as the amount of force that she must apply to move the cabinet. So her frictional force here, if we're talking about the static situation, is 575 newtons. That's how much frictional force exists there. In order for the cabinet to move, 575 newtons must be applied. The coefficient of friction is what's unknown, so I might say mu sub s for the static coefficient of friction. And now we need to multiply that by the normal force, okay? Well, the normal force is directly related to the weight of the filing cabinet. So figure out the weight of the filing cabinet, the normal force is equal to that. Well, we know the mass of the filing cabinet is 115 kilograms, so to get its weight, just take that times my old friend 9.8, and now I've got the normal force. So calculating that out, I'll end up getting a static coefficient of friction that is equal to 0.51. Now, there's no units on that, it's just a coefficient of friction, so I actually do not have a unit that goes with that, just 0.51 is sufficient. Okay, next let's look then at determining the coefficient of friction for the kinetic situation here. The kinetic being when it is moving. Alright, so same equation, but this time they tell us that once the filing cabinet is moving, it only takes 485 newtons to keep the cabinet moving at a constant velocity, and that's an important part of this too. Since we have a constant velocity, we are going to then be able to know that the frictional force and the applied force are equal to each other. So in this case, 485 newtons will then serve as our frictional force. That's equal to the coefficient of kinetic friction times, again, that normal force, which is, again, my 115 kilograms times my 9.8. So multiply that together, and for the kinetic friction coefficient, I get a value of 0.43. It's definitely less than the static friction, which we would expect because it took less force to keep the filing cabinet moving once it was already in motion. Alright, welcome back here. We've got a problem now dealing with friction, but also with something that is accelerating. So we have a worker pushing a 15 kilogram crate with an applied force of 65 newtons. The crate is going to experience some friction also as it slides along the ground, and we are given that the coefficient of friction in this case is equal to 0.42. We are asked to calculate the acceleration of the crate. So let's go ahead and start with a free body diagram of the crate. we know that the crate has a weight downward that is equal to its mass times acceleration, 9.8. They told us the mass of the crate is 15 kilograms, so that gives it a weight of about 147 newtons. There's also a normal force upward that the ground is providing that would also be equal to 147 newtons. Then there is an applied force that is equal to 65 newtons. That's the person pushing on the crate. And then there is going to be a frictional force that is opposing that applied force. We do not know the amount of the frictional force, but we can calculate it because we are given the coefficient of friction. So remember, our frictional force equation states that frictional force is equal to the coefficient of friction times the normal force. So let's go ahead and calculate that frictional force with a coefficient of friction of 0.42 and a normal force of 147 newtons. That gives us a frictional force equal to 61.7 newtons. Okay? And so I'll go ahead and throw that on my free body diagram as well. Now, the problem is asking us to calculate the acceleration of the crate. So to do that, we must figure out then what is the net force acting on the crate. Well, the net force is going to be the applied force minus the frictional force. So I take 65 newtons minus the 61.7 newtons, and that gives me a net force equal to 3.3 newtons. All right. Knowing that, now I can then substitute that into my equation for force equals mass times acceleration. Remember, I want to find acceleration here. So we will put that into the net force is equal to mass times acceleration, and we know the net force is 3.3 newtons. The mass of the crate, again, was 15 kilograms. And then I can solve for my acceleration, which in this case will end up equaling 0.22 meters per second squared.
Well, hello everyone, and welcome back to another problem with Sioux Falls physics teachers. Today we're continuing to look at friction, this time with an adjusted normal force. We have a student pushing a 70 kilogram couch with an applied force of 300 newtons. However, that force is directed down at an angle of 12 degrees with the horizontal. The couch moves with a constant velocity. Calculate the coefficient of friction between the couch and the floor that it is on. Well, first thing we will want, of course, is to draw a free body diagram of this situation. And again, notice they didn't specifically include that as part of the problem, but in a situation like this where you have a lot of different forces to keep track of, it is definitely worth taking a little bit of extra time to make that diagram. First, we'll find the weight of the couch directed straight down. Notice they've given us 70 kilograms, and at this point hopefully you're getting pretty good at just taking that 70 kilograms, multiplying times 9.8, and we get a force of 686 newtons. Now notice that most of the time we would have just real quickly put the normal force on there with an equal amount. However, this time we have this force over here to deal with. Okay, that force is in the angle of 12 degrees, which means it's in both the horizontal and vertical directions. And so that means that we're going to have to take it into account before we actually do the normal force. To do this, let's start by making kind of a separate free body diagram of this part. We have 300 newtons as our resultant. And notice that that's directed down and to the right. So we have really two components of that applied force. One is the component in the y direction, the downwards part. One is the component in the x direction, or the horizontal part. To do this, we've been given the angle of 12 degrees. So now we're back to a little bit of trig here. Doesn't really matter which order we do these in. We'll start with the y component, which is opposite. So the sine of 12 degrees would be opposite over hypotenuse, and that then would be opposite side, f sub y, over the hypotenuse of 300 newtons. And that gives us a vertical component of 62.3 newtons. Next, we can do the horizontal component, and the horizontal component is the adjacent side. And so in this case, then, we would be using the cosine of 12 degrees, and that's going to be equal to the x component over our hypotenuse, which is again 300 newtons, and that means that our x component is equal to 293 newtons. So now that we have those components, we can add them to our diagram. Again, 62.3 newtons is how much the student is pushing in the downwards direction, and then 293 newtons is how much the student is pushing in the horizontal direction. Now we're ready to do some work as far as finding the normal force.
Okay, so to find the normal force, we have to consider two factors: the weight of the couch and the amount of force that is being pushed in the downward direction as a result of the student. So our normal force now is going to equal the weight plus our F sub y. So adding the 686 newtons of weight plus the 62.3 newtons of F sub y, we get a new normal force then that is being supplied by the floor upward of 748.3 newtons. Now that we know that normal force, we are ready to calculate our coefficient of friction. Okay? So, frictional force is equal to mu times the normal force. Our frictional force is going to be equal to the force that is being applied in the x direction, the 293 newtons. It does tell us that this couch moves with a constant velocity, so we know that the applied force and the frictional force have to be equal to each other. So our frictional force is equal to 293 newtons. We're trying to find the coefficient of friction then, and the normal force that we calculated a minute ago, 748.3. And solving for mu, we get a coefficient of friction of 0.39.
Well, hello everyone, and welcome back to another Sioux Falls Physics Teacher's Problem, looking at another one of those inclined planes. Here we have a crate sitting on a ramp, and it does slide down with an acceleration. Calculate the coefficient of friction between the crate and the ramp. So to start with, we first need to take the information that they've given us and draw in a detailed free body diagram of the ramp. Okay, remember that we have weight of the crate going straight down, and we have 2.5 kilograms is the mass. We'll use 10 for gravity in this problem, which means that our weight is going to be 25 newtons directed straight down. Next, we want to then add in the components to this. Notice, first of all, that we're going to have one component that is directed down the ramp. That's part of the weight that's causing that crate to slide down the ramp and also causing it to accelerate in this case. And then we have another component of the weight that's directed perpendicular to the surface of the ramp, and that is the part that will function as the normal force. Our 40-degree angle, which is down here at the corner of the ramp, that is the same as this angle in our little triangle here. So the first thing that we want to do is find these components. The normal force, which is the adjacent side to 40 degrees, and then this component up here, and again there's a variety of different variables we can put there. A lot of times we'll use F sub g. It is a force of gravity. It happens to be a little different than the full 25 though, since it's just a component of gravity. So first thing, the normal force is adjacent to that 40-degree angle. So for an adjacent side, we would use the cosine of 40 degrees. And so the normal force would be the adjacent side divided by hypotenuse. And the hypotenuse for our triangle is that blue side, the weight of 25 newtons. And that means that we find that our normal force in this case is 19.2 newtons. Okay, we also want to go ahead and find the opposite component, and that would be, again, the sine, since it's opposite the 40-degree angle. Opposite side is that F sub g component divided by the hypotenuse, which is, again, our 25 newtons. And we find that that component turns out to be 16.1 newtons. So rather than think of our weight as being just simply 25 newtons straight down, we want to think of it as having two important parts. One is a component of 16.1 newtons pulling that crate down the ramp. And then secondly is a component of 19.2 newtons that is the normal force. Once we have these values, then we can go through and figure out exactly what that crate is going to do. Now notice that it does tell us the crate accelerates at a rate of 0.75 meters per second squared. If we think about the crate sitting on the ramp, the part that is pulling it down the ramp is this component here. 16.1 newtons is pulling it down the ramp. But it does have a certain amount of friction in the opposite direction that is acting against it. Now, because it is accelerating, we know that that friction is smaller than the 16.1. The first thing we need to do is figure out how much different the friction is from that 16.1. This will actually take us back to Newton's second law. Net force equals mass times acceleration. And in this case, we have the mass given to us at 2.5. We also have the acceleration at 0.75. And so we can find then that the net force is equal to 1.875 newtons. So if I compare the two forces acting on the crate, 16.1 newtons pulling down, force of friction going up the ramp, the net between those two is 1.875. So we can kind of write out the results of our free body diagram like this. Net force is equal to that weight component minus the force of friction. So in other words, the net force is equal to the difference between those two. We found that the net force needs to be 1.875. We have calculated the component of gravity at 16.1. And so if we do our subtraction, we find that the force of friction is 14.2 newtons. And that makes sense. If we put that up here on our diagram, 14.2 newtons, we can see then that the crate has 16.1 newtons pulling it this way, 14.2 newtons pulling it up the ramp, and that allows a small amount of net force which causes the acceleration. That kind of leads us to our last step, and this fortunately is the easiest one. Notice that the problem actually wants the coefficient of friction. Well, we have just found the amount of the friction force, and that is related to the coefficient through the equation friction equals coefficient times normal force. So now we have 14.2 newtons. And here is where it's important that we've already done some of our trig, because going back over here, we've calculated out what that normal force is. Notice it's important that the normal force is not the same as the actual weight. It's a component of that weight. So 19.2 goes in as the normal force, and that allows us to find our final answer for coefficient, which is 0.74. And again, remember that a coefficient is simply a ratio, so it does not have a label.
Hey, thanks for joining the Sioux Falls physics teachers here for a problem involving an inclined plane. We have a 400-gram crate located on a ramp. That ramp is at an angle of 25 degrees. We're given the coefficient of friction of the ramp, and the first thing we're asked here is to draw a free body diagram of the situation, and then ultimately to determine whether the crate is going to move or if it's going to remain at rest. So let's start with our free body diagram, okay? This is a key situation, one that we'll encounter quite a bit in various physics problems of an inclined plane. So, for the crate itself, we know that it's going to have several forces that are acting upon it. All right, let's start first of all with the weight of the crate, okay, which is going to be directed straight downward, okay? And then we also know that there is going to be components to that weight. There will be an X component that is directed along the ramp, as well as a perpendicular to that, a Y component. So we could call this WX and WY. Okay? In a minute here, we'll figure out the components of those different variations of the weight. What other forces, though, exist? Well, we also have a frictional force. So we know that the crate might tend to want to slide down the ramp. We'll determine here in a minute if it does actually move or if it remains at rest. But nonetheless, the friction, okay, would be supplied to the right or up the ramp there from in that direction. Would be opposing the potential motion the crate might have. Now, one other force we might consider also would be the normal force that the ramp is providing on the crate. That normal force is going to be equal to the weight in the Y direction. We often maybe kind of skip over this, but if we are drawing a true free body diagram of the entire situation, there would be a normal force directed upward that is supplied by the ramp onto the crate.
So now that we have our diagram, we do need to find amounts for the components. And again, notice that it's very important. This here is our right angle. So our hypotenuse of our little triangle is the weight over here directed in the downwards direction. So to start with then, our 25-degree angle, that is the angle of the ramp, is also the angle at the bottom of the triangle. And so we can start with the X component, and again, that component of the weight is opposite our angle. So in that case, we would be looking at the sine of 25 degrees. That is equal to the X component over the hypotenuse, which is the weight of the object. Now in this particular case, we have 400 grams, and so to find our weight, we would have 0.4 4 kilograms multiplied times 9.8, and that gives us 3.92 newtons for our resultant. So 3.92 newtons, and that means that our x component then is going to turn out to be 1.66 newtons. The second half of this is to find the y component, and that, of course, is right here. It's the adjacent side to our angle over here. So this time we would be using the cosine of 25 degrees. That is equal to our y component divided by the hypotenuse, which is again 3.92 newtons. And then if we solve for our component, we get 3.55 newtons for that component. Now, why do we need both of these? Well, remember that it is this component here, this component that is perpendicular to our ramp, that is what tells us how much the normal force is. So once we have this 3.55 newtons, that would be the same as the normal force. The coefficient of friction is given to us at 0.55, so we can use our friction equation, coefficient times normal force, and we have 0.55 times the normal force, which is 3.55 newtons, and we end up with a force of friction of 1.95 newtons. Now, a couple of things about this. That tells us then, if we were looking on our diagram, we had our friction directed up. So here's our arrow opposing the motion. That amount that we just calculated is 1.95 newtons. Now, if we take a look in the other direction, we have our x component that's going down. Earlier, we calculated that at 1.66 newtons. Now, one thing that's kind of important here, the first part of the question asks us to determine whether the crate will move or remain at rest. The two forces determining that are the two that move up and down the ramp. Okay, here we have 1.66 newtons as a component of the weight trying to pull the crate downwards. On the other side, we have a force of friction of 1.95 newtons that is acting to oppose that. And since the friction is greater than the weight that is pulling downwards, we find out that our crate would remain at rest. One other thing that we really should change here, notice that if you look at our free body diagram right now, it looks a little bit strange because we have 1.66 newtons going down. Friction was at 1.95 going up the ramp. If we really followed that, it would seem like friction would be grabbing our crate and pulling it right up the ramp. We know, of course, that's not the case, and that's why I kind of added in over here, when you do the force of friction, technically these all should have been less than or equal to signs. So the force of friction is less than or equal to 1.95 newtons. 1.95 is the maximum friction we could have in this case. But if I'm drawing a true free body diagram, I really should not put that at 1.95. Instead, I will only use as much friction as is needed to counteract the weight pulling down the ramp. So 1.66 newtons is the amount that is actually used. It does not need that maximum possible of 1.95.
Okay, boys and girls, let's tackle a culminating problem for this chapter. This kind of puts together all the ideas we've dealt with in this chapter into one gargantuan problem. It's an Atwood machine on an inclined plane. So in this problem, the Atwood machine is constructed of a crate of 1 kilogram connected to a mass of 2.5 kilograms on a ramp inclined at an angle of 25 degrees. The coefficient of friction between the crate and the ramp is 0.45. That's our mu. Calculate the acceleration of the objects and the tension in the cable when they are released. In other words, as soon as we let go, this is going to move. It's either going to move down or up, something we don't know yet because of the weight hanging over the edge. So to start this problem, we probably need to find out what that friction is. So let's break this part of the problem right here and address that friction component first. To do that, we need to find the different components and the normal, because we know that friction is equal to the Fun equation. Friction equals mu times the normal. So how will we find that normal? Well, we know a couple things. The crate has weight. We can call it W for weight, or we can call it F of G. Either one is acceptable. That's a force downward. Some of that force is going to cause the normal. Some of that force is going to cause it to move in this direction, assuming there was no other weight acting on it. So the normal would go upwards. Remember, the normal is always perpendicular to the surface. And then we have a component that's going this direction along the ramp. And this component here is what actually causes it to accelerate. If there was no weight hanging off the other end, that might cause it to move in the other direction. So let's draw this triangle. And when we go ahead and draw this triangle, our gravity is what's causing it. That's the weight, F of G. Our F of X is here. And then this is the normal here. This component right here. It's actually the negative of the normal. And it's actually the F of Y. Because what I've actually done is change my coordinate system to make this problem easier. This is my Y direction. This is my X direction. Now, a couple quick things. This angle right here is not the top angle of my triangle. It's actually this angle. And we have to keep that in mind. So when we're thinking this through, we have to think in terms of that. The other thing is, we know what F of G is. And F of G is very easy to solve because F of G is simply mass times gravity. Let's use 10 for gravity just to make our life easy. We know our mass of the crate is 1. So we got 10 times 1. That will give us a mass of a force of gravity of 10 newtons downward. Very straightforward on that. So we've got this side right here, which is 10 newtons. We know the angle, and that's sufficient information for us to discover both F of X and F of Y, which is really going to be our normal. So let's go ahead and solve for that F of Y. By the way, the reason the F of Y is the normal is it's the force in the opposite direction, so that these forces add up to 0. The normal plus this F of Y have to equal 0, or the crate would fall through the ramp. Something we don't really want. So let's go ahead and solve for that. You'll notice the F of Y is actually on the adjacent side. That makes this cosine. So cosine of the angle has to equal the F of Y all over the F of G. When we plug in the numbers there, we've got cosine of 25 has to equal the normal all over 10. And when we solve for that, my normal, I'm using n for normal, ends up being 9.06 newtons. Now that we have the normal, we can use that Fun equation and solve for our force due to friction. So we got friction equals 0.45, which is my mu, times my 9.06, which is my normal, and we're going to end up with a friction value of 1.95 newtons. Now I've used a italicized F for friction, but the truth is friction is simply another force. So I could have written this as the force due to friction with a little f in the bottom. And this will make sense when we go to the next step where we're talking about forces. So keep that in mind. Friction is a force. We've got the friction. Now we can go to the next step of the problem.
Okay, the next thing that we want to do is finish off our free body diagram. And again, if you look over here at the crate itself, we can see some of the important parts of the forces on the free body diagram. We already have the weight, which represents the resultant weight, the 10 newtons in the downwards direction. And then remember that that weight is divided into two components. One is in the x direction here. That's the component of weight that would act to pull the crate down the ramp. The second one is one that we've already used, and that's the component that goes perpendicular to the surface. That would be the F sub y, and that's what represented the normal that we just used to find the friction. Now before we do a free body diagram though, we also need to find this horizontal component. So we're going to repeat some of the trig here, only this time the horizontal component is opposite the angle that we know. Again, remember 25 degrees is down here. So this time we'd be using the sine of our angle is equal to the x component of weight divided by the resultant of weight. We know that that angle is 25 degrees. And the weight itself is 10 newtons, and so that means that we can solve for the x component of that force, and that turns out to be 4.23 newtons. Okay, now that we have that component, we are ready to start our free body diagrams. Now notice that our free body diagram for the crate already has quite a few things on it. The weight is going downwards. We've divided it into two components, the F sub x and the F sub y. We also see the normal. There are two more forces that we need to add. One is that force of friction that has already been calculated. And again, remember that at this point we're going to need to make a decision as to which direction we think the weight is going to travel. In the end, if we find out that we get negative values, we may need to go back and reverse that direction. But right at this point, let's assume that the crate is traveling up the ramp with an upwards acceleration. If that is the case, then that means that the friction would act to oppose that motion, and so the friction would be acting back down the ramp. And we calculated that amount earlier as 4.08. The last force to add is the force that's causing this crate to move in the first place, and that is the tension from the string pulling it up the ramp. And then that tension will be attached to the weight on the other side, and that weight we assume is going to be falling. That allows us to move to a free body diagram of the 2.5 kilograms that is the mass that is attached here. And we have a little free body diagram ready to go down here at the bottom. This one is a much simpler free body diagram than the crate. It certainly does have weight in the downwards direction. To calculate that, we have a mass of 2.5. Again, we'll use 10 for gravity, which gives us a weight of 25 newtons. Okay, it also has tension in the upwards direction. And again, remember that for right now, we're going to assume that this weight is traveling downwards with a downwards acceleration. So if that is the case, then the tension in the upwards direction should be less than the weight. Now that's one of our unknowns. We don't know what that tension value is, but we are going to assume for now that it is smaller than the 25 newtons of weight pulling down. Now we are ready to write our system of equations. And remember that basically the idea of our system is that we want to write the net force acting on each object. So we'll start with our 2.5 kilograms since we just finished up that diagram. We have a weight of 25 newtons going down. The tension, which we assume to be smaller, is going up. So the net force acting on that object, the 2.5 kilograms, would be 25 newtons minus the tension. Whatever is left between those two would be the net force acting on that mass. That, we know from Newton's second law, is also equal to mass times acceleration. Well, acceleration is again one of our unknowns, but the mass is a known value at 2.5 kilograms multiplied times A. So now we've written our net force equation for the 2.5 kilogram mass. Now we have one that's a little bit more complicated, and that is the net force equation for the crate. One thing we need to keep in mind is that as we look at our crate, the direction of motion is up and down the ramp. So the only forces we need to deal with are the forces that go up and down the ramp. The normal force, for instance, up there at the top, or that weight component, F sub y, directed into the ramp, those should be canceling each other out, and they should not have anything to do with the motion of the crate. So again, if we assume that our crate is traveling in the upwards direction on the ramp, then we would have three forces to account for in our free body diagram. We have the tension here, that's pulling it up. In the opposite direction, we have friction acting against motion. And this is an easy one to forget, but we also have a component of its weight that is also acting against that tension. So when we get to writing our net force equation for the crate, we're assuming for now that tension is the greatest and that it is greater than the friction and the x component of weight combined. So we're saying that if the tension is larger than those two, then that crate should be moving up the ramp. That again is the net force, and we know that net force is equal to mass times acceleration. The mass of the crate is 1, and the acceleration is our unknown. Finally, we are now into doing the algebra. And again, at this point, there's a variety of different ways that you could do this. We'll go ahead and use substitution, but there would be a couple of other ways that you could do this as well. First, we'll put in our numbers for the crate. The force of friction was 4.08. The x component of the weight was 4.23. And mass times acceleration is still 1 times a. We can then take this equation here and solve it for tension. This would basically be equal to tension equals 1a, moving the 4.08 and the 4.23 to the other side. We have 1a plus 8.31. And then to substitute, we would take our first equation and we would substitute in for t, so 25 minus this part here goes in for t, 1a plus 8.31. That is equal to 2.5a. Now at this point, we're going to assume that you can do the algebra on that. Solving for a, we get an acceleration value of 4.77 meters per second squared. Notice that the fact that that is a positive value is important because it means that we were correct in our guess of direction on these two. Then we can use either one of the equations to solve for t. Notice that this one here would be pretty simple because it's just 1a plus 8.31. Using that to solve for T, we get a tension of 13.1 newtons in the string.